I just want to share my screen. For today is about sampling and sampling distribution. So specifically covered the random sampling. No? Some researchers aim to study, describe, and infer patterns of behavior, properties, and characteristics about a population. Sometimes, they intend to study in a very large scale, and because of the fact that we cannot study a very large population due to feasibility, impracticality, and inconvenience, that is why we must select a representative sample from the population. In this discussion, sampling techniques that help researchers select samples that would represent true inferences about the population where these samples came from. Now, what is population? It is the group you want to generalize. So it consists of all the members of the group you are interested in. Sample is the subset from the population you want to examine. A population commonly contains too many individuals to study conveniently and practically, so an investigation is often restricted to one or more samples drawn from it. A well-chosen sample will contain most of the information about a particular population parameter, but the relation between the sample and the population must be such as to allow true inferences to be made about a population from the sample. Okay, so sampling is a process used in statistical analysis in which a predetermined number of observations are taken from a large population. There are various sampling methods that allows all the units in the population to have an equal chance of being selected. And the sampling methods are follows. So, in simple random sampling, each element of the population has an equal chance of being selected. There are no rules that dictate where and how you will start the selection process as long as you do not intentionally look for a specific number. In this method, the samples can be selected through lottery method. So every member is assigned a unique number, and these numbers are put in a jar and thoroughly mixed. After that, the researcher picks some numbers without looking at it, and those people are included in the study. Next, of course, is the use of table of random samplings. This table consists of a series of digits 0 to 9 that are generated randomly. The numbers are arranged in rows and columns and can be read in any direction. All the digits are equally probable. So, to determine the desired number of samples needed give a certain number of population, there are different formulas can be used, and one of which is the common or the Slovin's formula. So, we have here a Slovin formula. So, n is equal to uppercase n over uppercase n uh, margin of error squared, no? So, as what we have here, lowercase n is a sample size. E as what we have here, no? No, this n, of course, is for sample size. This E, no, for margin of errors, squared, no? As you can see here. Then uppercase N is the population. That is uppercase N, and of course the uppercase in here, which identify as population size. So, for example, so we have a given already here about, we have a given already, no? So, N is unknown, for example. So, that's what we have here. Then, margin of error is 0.05 or 5%. Then, number or population size is 1,000. For example, you have a 1,000 student and you want to find out how many, no, sample size possible to undertake to answer all your questions based on your research. So for us to get the sample size, what we're going to do is to apply the Slovin's formula, as I mentioned. So as what we have here, no, direct substitution, that is 1,000 because n, uppercase is n is 1,000 based on the given, that's what we have here. Then 1,000 multiplied by 0.05 because our margin of error is 0.05 squared. Then, of course, what we're going to do first is to multiply the squared 0.05 to square, that is 0.0025. Then, of course, 1,000 multiplied by 0.0025, that is 2.5. Then, n is equal to 1,000 over 2.5. So, the answer is, or the sample size is 400. So, instead of considering 1,000 participants of the study, using the Slovin's formula, we can get 400 as a sample size for your study. Now, we have also what we call systematic random sampling. This can be done by listing all the elements in the population and selecting every kth element in your population list. And this is equally precise as the simple random sampling. It is often used on long population lists to determine the interval to the use in identifying the samples to who will participate in the study. Use the formula K is equal to population divide sample size. Example. So in population, N is equal to 2,000. Sample size, for example, is 500. So K is equal to 2,000 over 500 is equal to 4. No? So use a table of random numbers to determine the starting point of selecting every fourth subject. So with list of the 2,000 subjects in the sampling frame, go to the starting point and select every fourth name on the list until the sample size is reached. Probably, we'll have to return to the beginning of the list to complete the selection of the sample. Because for example, if you have a 2,000 population, no, targeted, no, then you wanted to have a sample size of 500. How will you get the 500? No? The 500 respondents or the 500 participants of your study on the available 2,000. No? So what you're going to do, as what we have here, you may apply the systematic random sampling. Okay? So for example, you just list the 1 to 2,000 name. Then every count 1, 2, 3, 4 you get. 5, 6, 7, 8 get. 9, 10, 11, 12 get. Every fourth, no? Based on the given formula. Another, of course, is the stratified random sampling. This can be done by first dividing the elements in the population into strata, and then samples are randomly selected from each stratum, ensuring that each selected element is appropriately represented in the total population. Sampling fraction, n or lowercase n divided by n. Desired sample size divided by the population size. For example, no? Example again. Assume you have a population of 1,000 students with 500 from grade school, 300 from high school, and 200 from senior high school. Determine how many samples do you need, or you can use the Slovin's formula or any other formula for computing the sample size. In these examples, the Slovin's formula is used and a sample size of 400 is computed. So to get the samples from each stratum, divide 400 by 1,000. And the answer is 0.4, right? So multiple point, 0.4 is multiplied per stratum. So for example, as what we have here, for grade school, we have 500 times 0.4, that is 200 sample size. It means to say that from grade school, you need to get at least 200. Then for junior high school, 300 divide 0.4. So you can get the 0.4, that is, of course, 120. Uh, 0.4, again, times 200, that is 80. 0.4, so therefore, 1,000, you can get 400 sample. Okay? So, in a stratified sa random sampling, of course, we can say that we can get no equally, no, a number of participants of the study based on the given stratum. So, equally distributed from the grade school, junior high, and senior high. Number 4 is the clustered sampling. A multi-stage sampling method adopted when it is either impossible or impractical to compile an exhaustive list of elements found in the stage in the target population. The whole population is subdivided into clusters or groups, and random samples are then collected from each group. Example, a researcher wants to survey about academic performance of high school students in the municipality of Batangas. He can divide the entire population into different clusters or barangays. Then, the researcher select a number of barangays depending on his research through simple or systematic random sampling. The researchers could draw random samples from the selected barangays through simple random sampling or take them all. More example actually, no? Simple random sampling in a recent research that was conducted in a private school, the subject of the study were selected using the table of random sampling. The stratified sampling, a teacher who is conducting a research on the effects of using mobile phones in teaching mathematics decided to divide her student into male and female, and then she selected students from each gender group. For systematic sampling, the school office personnel gave the researcher a list of 2,000 grade 12 students. The researcher selected every 25th name on the list. For the cluster sampling, a researcher surveyed all COVID-19 patients in each of the 10 randomly selected hospitals in National Capital Region. Okay, now, lesson number 2 is about parameter and statistics. In this discussion, you learn about random sampling, a process done in selecting an unbiased representative sample from a population. This time, you will be introduced to the measures involved in the population and sample. Measures from a very large population are impossible to obtain, especially if your resources are limited. This brings us to other measures which are from the representative samples, and this discussion will help you identify measures about population and sample. A measure that describes a population is called parameter. A measure that describes a sample is called statistics. Okay? In population parameter, mean is represented by represent variance and represent standard deviation. In sample statistics, mean is represented by uh, represent variance and represent standard deviations. Data from a sample are used to calculate statistics. And statistics are estimates of the corresponding parameters. Now, example. For example, parameter is 50% of the 24 Philippine senators agreed to support a certain measure. A statistic, a researcher found out that 25% of the students in Philippines reported to have internet connection at home. The example indicates a parameter since there are only 24 senators in the Philippines, right? Researchers cannot ask millions of students if they have internet connection at home. So they take samples from the target population and calculate. Again, for example parameter, the example indicates a parameter since there are only 24 senators in the Philippines. Researchers cannot ask millions of students if they have internet connection at home, so they take samples from the target population and calculate. Parameter includes population mean, population variance, and population standard deviation. While statistics is a measure that describes a sample, statistics include sample mean, sample variance, and sample standard deviation. Now, we have here a sample distribution of the sample means. You learned in the previous lesson about discrete probability distribution and continuous probability distribution. In this topic, you will learn how to identify and construct sampling distribution of sample means. You also learn on how to find the mean and variance of the sampling distribution of the sample mean. So, if you list all the possible sample of size 3 drawn from a population of 4 with elements 2, 3, and 4, you will have 9 samples. The table shows the 9 samples and their corresponding mean. So, as what we have here. So, we have sample 2, 2, 2, 3, 2, 4, 3, 2, 2, 3, 3, 3, 4, 4, 2, 4, 3, 4, 4. That is 9. And the possible sample mean, that is 2, 2.5, and so on and so forth. Because 2, as what we discussed before, 2 plus 2 is 4. Divide 2, that is 2. 2 plus 3, 5. Divide 2, that is 2.5. 2 plus 4 is equal to 6. Divide 2 is equal to 3, and so on. Then, this let us learn how to make a probability distribution of the sample means. So, we shall call this distribution the sampling distribution of sample means. So, as what we have here, we have the sample mean here, and we have a frequency at this time, no? So, we have 2 as a sample mean, frequency is 1. So, therefore, the probability of mean is 1 over 9. This one, that is 2, 2 over 9. Since frequency is 3, 1 over 3. Then 2, that is 2 over 9. Then 1 is 1 over 9. So, how do we come up with this? No? Because 9 over 3 is equal to 3, right? So, therefore, 3 over 9, that is 1/3. Okay? So, because as you can see here, the 2 over 9. So if we're going to do this one, that is 3 over 9, right? But 3 over 9, that is 1/3. So instead of writing 3 over 9, that is 1/3. Okay? A sampling distribution of sample means is a probability distribution that describes the probability for each mean of all samples with the same sample size. Now, finding the mean invariance of the sampling distribution of sample means. The following are formula needed to complete the mean, variance, as standard and standard deviation of population, and mean, variance, and standard deviation of the sampling distribution of a sample means. So based on the given formula here for mean for population, mean for sampling distribution of sample means. This will be the formula for variance in population, and this will be the formula for sampling distribution of sample means. This will be the formula for standard deviation in a population, and this will be the formula for sampling distribution of sample means in getting the standard deviations. Okay. Sampling with replacement. So based on the given example, consider a population consisting of the values 2, 5, and 8. What we're going to do is to compute the population mean, compute the population variance, find the population standard deviation, and list all the possible samples of size 2 with replacement in their corresponding means. Find the mean of the sampling distribution of the sample mean, find the variance of the sampling distribution of sample means, and find the standard deviation of the sampling distribution of sample means. So, as what we have here, if we compute the population mean, we can get 5. Okay, based on the given formula, and of course, through direct substitution. Our summation, that is 2 plus 5 plus 8, based on the given. For us to get the population mean, right, over 3, because we have only 3 sample, okay, or 3 number of occurrence. So, if we are going to add this one, that is 15 over 3. So, therefore, our population mean is equal to 5. Compute the population variance. So, we have 2, 5, and 8. So, x minus population mean. So, 2 minus 5, okay, because our population mean is 5, no? 2 minus 5, that is negative 3. 5 minus 5, that is 0. And 8 minus 5, that is 3. Now, how about if we're going to get the x minus population mean? So, then squared. So, for us to get, of course, what we're going to do is negative 3 squared. Because this will be the result of this, no? X minus population variance, no? Squared. So if we're going to square negative 3, that is 9. Squared 0, that is 0. Squared 3, that is 9. So summation of x minus population variance squared is equal to 18. Because x minus u squared is 18. 9. So squared, that is 18. Right?
Sir, pwede po mag-question?
So here is the population mean in post na lang po sa chat box yung question para tuloy-tuloy tayo.
Okay, sir. Pwede po.
No, so we have 6, no? So because in getting the standard deviation, no? So we need to define first, no? So find the population standard deviation, that is, this will be the formula. So theta is equal square root of 6. Therefore, the standard deviation is 2.45. So list all the possible samples of size 2 with replacement in their corresponding means. So as what we have here, for example, no, we have 9, no, as 9 observations. Then if we're going to get the mean of this given, that is 2, 2, that is 2, 2, because if we're going to add 2 plus 2, divide 2, that is 2. 2 plus 5 equals 7, divide 2, 3.5. 2.8, o 2 to 8, that is 10. 10 divided to 5, and so on and so forth. Now, find the mean of the sampling distribution. So, with this, we could able to get 45. The summation of mean is 45. Find the mean of the sampling distribution of means. So, based on the given formula, summation of mean over n. So, as what we have a while ago, we have 45, the summation of mean, over 9, because we have 9 observations. So, 45 over 9, that is 5. So, therefore, the sampling distribution of sample mean is equal to 5. Now, find the variance of the sampling distribution of means. Okay? So, as what we have here, so we can get this, of course, same as what we did. So, based on the given, we have 5, no? So, 5 minus 2, 2 minus 5 rather, that is negative 3. 3.5 minus 5, that is 1.5. 5.5 minus 5 is 0. 5.5 minus 3.5. 3.5 minus 5, that is 1.5, and so on and so forth. Then for us to get this one, that is negative 3 times negative 3, that's 9. Negative 1.5 times negative 1.5, that is 2.925, and so on and so forth. Then, summation of mean, that is squared, that is 27. Find the variance of the sampling distribution of means. So, direct substitution, then we could able to get the variance of the sample distribution is equal to 3 for sampling distribution of sample mean. Find the standard deviation. So, direct substitution, that is 3. Square root of 3, that is 1.73. So, therefore, the standard deviation of the sampling distribution of sample mean is 1.73. Okay, how about sampling without replacement? So, consider a population consisting of the value 1, 3, and 5. So, same as what we did a while ago, compute the population mean, variance, and standard deviation. Then, all possible samples of size n equals to 2 without replacement and their corresponding mean. Find the sampling distribution of sample means, variance of sampling distribution of sample means, and find the standard deviation of the sampling distribution of the sample means. Compute the population mean. So, based on the given, we have 9. So, 1 plus 3 plus 5, that is 9 over 3. So, therefore, our population mean is equal to 3. Compute for the population variance based on the given formula earlier. So, why 8? Because that is n minus 1, is n minus 1. Summation of x sub u, that's n. That is 8 over 3. So, therefore, we had 2.67 as our population variance. Find the population standard deviation. So, direct substitution. A while ago, we have 2.67. So, square root of 2.67, that is 1.63. Therefore, the population standard deviation is 1.63. List all the possible samples of size 2 with the replacement and their corresponding mean. So, same as what we did earlier, 1 plus 3, that is 4, divided 2, that is 2. That will be the sample corresponding mean. And so on. Find the mean of the sampling distribution of means. Okay, so as what we have here, we can get summation of mean is 18. Okay, because if we're going to add 2 plus 3 plus 2 plus 4 plus 3 plus 4, that is 18. And that is summation of mean. So how can we get this 2, 3, 2, 4, and of course, again, same. 1 plus 3, 4, divide 2, that is 2. 1 plus 5 is 6, divide 2 is 3. 5 plus 1 is equal to 6, divide 2 is equal to 3, and so on. Now, direct substitution for us to get the mean of sampling distribution of a sample mean. So, summation of x, that is 18, over 6. because we have 6 observations, as you can see here. So, therefore, our sampling distribution of sample mean is equal to 3. So, find the variance of the sampling distribution of the mean. So, same as what we did earlier. So, we can get this one, no? That is our given a while ago, that is 3, right? So, 2 minus 3, that is negative 1. 3 minus 3 is equal to 0. 3 minus 2, 2 minus 3, that is negative 1, and so on. Then, squared, again, negative 1 multiplied by negative 1, that is 1, and so on. So, therefore, if we're going to add 1 plus 1 plus 1 plus 1, that is 4. So, therefore, our variance of sampling distribution is 4. Then, direct substitution for variance of sampling distribution of a sample mean. So, based on the given formula, that is 4 over 6, or our variance of sampling distribution of sample mean is equal to 0.67. Okay, so for us to find the standard deviation of the sampling distribution, a while ago we can get the 0.67. So if we're going to get the square root of 0.67, we can get, of course, 0.82. This will be the standard deviation on the sampling distribution of sample means based on the given earlier. Now, the example above, by comparing the means and the variance of a population, the sampling distribution of the sample means. We can summarize the properties of the sampling distribution. We need to take note that if all possible sample of the size that can be drawn from the population of size n with mean invariance, then the sampling distribution of the sample means has the following properties. Of course, we have with replacement, wherein the mean of the sampling distribution of mean is equal to the mean of the population. The variance of the sampling distribution of means is equal to the population variance divided by the size of the samples. Then the standard deviation of the sampling distribution of mean is equal to the population standard deviation divided by the square root of the sample size of the samples. For without replacement, the mean of the sampling distribution of mean is equal to the mean of the population. The variance of the sampling distribution of mean is equal to the population variance divided by the size of the sample mean. And the standard deviation of the sampling distribution of means is equal to the population standard deviation divided by the square root of the sample size of the samples. So, to summarize the previous discussion, before we proceed to this one, the probability distribution of the sample mean is called the sampling distribution of sample means. A sampling distribution of sample mean is probability distribution that describe the probability for each mean of all samples with the same sample size. If all possible sample of size that can be drawn from the population of size n with mean of n variance, then the sampling distribution of the sample means has the following properties. And so on. Now, we may proceed to the sampling distribution of the sample means using the central limit theorem. The central limit theorem states that the sampling distribution of the mean approximate a normal distribution with a mean and a standard deviation of the sample size n of the random samples is large enough. Now, illustrating the central limit theorem, so given a die it has 6 spaces in which each space has either dots x is equal to 1, 2, 3, 4, 5, and 6. Given it as the population, consider the sample size of n is equal to 1 and 2 if n is equal to 1. So, as what we have here, based on the given situation, that is, for us to get the mean, we are going to add 1, 2, 3, 4, 5, 6 over 6. Then we can get 3.5. So, note, computation per population mean in sampling distribution mean is the same for n is equal to 1. So, for us to get the variance, so we can get 2.92. Okay? Standard deviation, same scenario. So, given a die, it has 6 spaces again. Therefore, again, the computation of population mean that is 3.5. So, therefore, we can get 2.92 also. Now, so standard deviation. We have a sample 1 to 6. The mean is 1, 2, 3, 4, 5, and 6. Then the probability is 1 over 6. So, as what we have here, we have n is equal to 1. Then we have 0.18, 0.16, 14, 12, and so on and so forth. Now, how will be able to interpret the situation or scenario? The population mean in sample distribution means are both equal, which is 3.5. It has a variance of approximate 2.92 and a standard deviation of approximately 1.71. And since all samples have the same probability of 1 over 6 or 16 over 6, the trend of the histogram is like a flat line horizontally. So, as what we have here, if n is equal to 2, the population mean that is 3.5. The sampling distribution mean, same, that is 3.5. And our variance is 1.46. And to get the standard deviation, that is 52.5 over 36, that is 1.21. So the table shows a total of 36 samples and the probability of each are as follows. Then this will be the given central limit theorem graphs. Okay? So this will be the first topic for this evening. So we may proceed to the correlation analysis, of course. Good day, everyone. So our topic for today is about correlation analysis. So this module, as part of the response in crafting the alternative delivery module learning resource of the Commission on Higher Education and Department of Education in the Philippines, is made for the students who took up statistics and probability subject. The research focuses on topics under correlation analysis, which include constructing scatter plot, computing the Pearson product coefficient, and solving problems involving correlation analysis. You are also advised to use application like Excel in your computer in accomplishing some objectives. So this is to make you enjoy the comparison of manual computation and use of formula in the computer application. This lesson starts with a assessment, no, on how much your knowledge you have about the lesson. At the end of the assessment, ensure that you gain an understanding and skill on the objective set. Again, this module is created and crafted by the Department of Education for a curriculum guide. So in this lesson number 1, under correlation analysis. Now, at the end of this lesson, you are expected to illustrate the nature of bivariate data, construct a scatter plot, and describe shape, the form, the trend, the direction, and variation or the strength based on the scatter plot. Now, what is bivariate data? In statistics, this is classified according to how many variables are in a particular study. So when you conduct a study that looks at a single variable, that study involves an univariate data. So for example, you study a group of students to find out their average grades. While bivariate data is when you are studying two variables. Again, univariate data involves in a single variable. For bivariate data, it is used when you are studying two variables. Okay, so these variables are compared to find the relationship between them. So for example, age might be one variable and weight might be another variable. Another is when you want to find out the temperature in the ice cream sales. Using correlation analysis, we can find out the relationship of variables in the bivariate data. Many businesses, marketing, and social science questions and problems should be solved using bivariate data sets. For instance, is there a link between child obesity and family income? And this is where correlation analysis is helpful. The correlation analysis is a method of statistical evaluation used to study the strength of a relationship between two numerically measured continuous variables, like as I mentioned, height and weight. And this particular type of analysis is useful when the researchers want to establish if there are possible connections between the variables. So, how about the positive correlation? So, both variables move in the same direction. So, in other words, as one variable increases, the other variable also increases. That is positive correlation. As one variable decreases and other variable also decreases, an upward trend and point indicates is positive correlation. So again, if one variable increases and the other variable also increases, that is positive correlation. As one variable decreases and other variable also decreases, that is also a positive correlation. An upward trend in points indicates a positive correlation, either downward or upward. We have negative correlations. No? The variables moves in opposite direction. As one variable increases, the other variable decreases. So as one variable decreases, the other variable increases. A downward trend in points indicates a negative correlation. So example, as what we have here, academic performance versus number of hours watching TV, stress versus job performance. We have also what we call, as I mentioned, this will be a negative correlation, right? So this will be an example already, no? The variables move in opposite direction. As one variable increases, the other variable decreases. Or as one variable decreases and other variable increases. How about the zero or no correlation? It means that there is no apparent relationship between the two variables. For example, shoe size versus salary. socioeconomic status versus grades. That is actually no correlation at all. Now, the strength of a correlation is determined by each numerical value. It may be perfect, very high, moderately low, very low, and zero. So, this diagram actually shows some example of scatter plots and correlations. So, we have the strong positive correlation as you can see here. We have the weak positive correlation. We have strong negative correlation. We have weak negative correlation. We had moderate negative correlation and no correlation at all. So for those who want to use a creating scatter plot in spreadsheet or Excel, no? So what interesting is you can create your scatter plot from your data using Excel. So how? What you're going to do, of course, select the worksheet range that contains the data. So as what we have here, no? We highlighted, no? This one. It's already highlighted. Click on the Insert tab. So, find the Insert tab. Click the XY or Scatter Chart command button. Then, select the chart subtype that doesn't include any lines. Then, confirm the chart data organization. Annotate the chart if appropriate. So, add those little flourishes to your chart that will make it more attractive and readable. So, for example, you can use the chart title and axis title buttons to annotate the chart with a title and with description of the axis used in the chart. But if you want to add a trend line, click Add Chart Element, menus, Trend Line command button. So, as what we have here, based on the given example. No? So, this will be the step, and this will be the possible output right after following this instruction. Our next lesson is about person, product, movement correlations. So, it will discuss on how to calculate the person's sample correlation coefficient and then how we'll be able to solve problems involving correlation analysis. Of course, the most common coefficient of correlation is known as the person-product moment correlation coefficient, or in short term, that is persons R. It is a measure of the linear correlation or the dependence between two variables, x and y, giving a value between +1 and -1. It was developed by Carl Pearson from a related idea introduced by Francis Galton in the 1880s. When conducting a statistical test between two variables, it is a good idea to conduct a person correlation coefficient value to determine just how strong the relationship is between the two variables. So if the coefficient value is in the negative range, then that means that the relationship between the variables is negatively correlated. Or as one value increases to other decreases, if the value is in the positive range, then that means the relationship between the variables is positively correlated, or both values increases or decreases together. Again, if the coefficient value is in negative range, then that means that relationship between the variables is negatively correlated, or as one values increases, then the other decreases. But if the value is in the positive range, then that means the relationship between the variables is positively correlated, or both values increase or decrease together. So we have here to determine the strength of the computed R. So we have here the no association or correlation. We have here the very low correlation. We have here the moderately low correlation. that is 0.50 to 0.75, that is moderately high. 0.75 to 1, that is very high or strong correlation. And more than 1, that is perfect correlation. So, most of spreadsheet editors such as Excel, Google Sheets, and OpenOffice can compute correlation for you, no? So this will be the illustration as what we have here, no? Using the Excel, click on the empty cell where you want the correlation coefficient to be entered, then enter the formulas. So as what we have here, so we use displays, no, to display the person R. So then we just simply type the person. Then of course the array one, this one, no, from 7 to, you just simply highlight this one. Then comma, as what we have here, that is A2, no, this because this is this is 2, then column A, no, so column A, that's why A2, as what we have here, that is A2, no, colon, then up to A7, right? So A2, this one, A2 to A7. Then comma, then array 2, that is B2, that is B2 up to B7. That's as what we have here, B2 colon to B7. But it's separate by comma. Then press enter. Then automatically we could able to get the person R. It's too easy, right? So, as what I've mentioned earlier, for example, above the person correlation coefficient is 0.076. Okay? That is below 1. So, that's it. Okay, so this will be the correlation analysis. So, this time, we may proceed to the regression analysis. So as you can see, I will give an example, and at the same time, a step-by-step procedure, I will be able to come up with the result for getting the for example, as what we have a while ago, the correlation coefficients and others. Topic for today is about regression analysis. So in this discussion, I will assist you in understanding the slope and y-intercept of regression line, which will be composed of a calculation and interpretation of the slope and y-intercept of a regression line. After going through this discussion, you are expected to be able to calculate and interpret the slope and y-intercept of the regression line. So to achieve the objective of this module, you need to understand its content comprehensively and of course, follow some instruction provided in different activities. In the previous lesson, you learned that when we study variable relationship, we first need to collect our data and use correlation to determine if linear regression exists. We need to understand that correlation analysis is the process of finding how well the line fits the observation such that all observation lie exactly on the line of best fit. The correlation is considered to be perfect one or unity. The correlation coefficient, as what we discussed last time, or the persons are product moment correlation coefficient. It is a numerical measure of the linear relationship between two variables usually labeled x and y. So while in regression, the emphasis is on predicting one variable from the other. In correlation, the emphasis is on the degree to which a linear model may describe the relationship between the two variables. The regression line is also called as the line of best fit, no? So its significance is enabling us to interpret data trends and help us in making predictions based on that data, the latter which is to be discussed later. So again, please take note that in doing regression, you first need to consider the following assumptions. There exists a relationship between the variables, and relationship is tested to be significant. The stated conditions are necessary to be first met, otherwise doing a regression analysis would be totally pointless. A scatter plot, no? It is a way of illustrating a line of best fit. The, the figure shows a scatter plot of a data of two variables. As you've noticed that several lines can be drawn on the graph near the points. With this, you should be able to draw the line of best fit. Best fit means that the sum of the squares of the vertical distances from each point to the line is at a minimum. So based on what we have here, we have the predictive value and of course the observed value. The equation of a regression line. Going back in our algebra concept, an equation of line is given by where stand for the slope and b for the y-intercept. Similar, an equation of a regression line is between y sub 1 is equal to a plus bx, where b is the slope and a is the y-intercept. So furthermore, the concept or the corresponding formulas for the y-intercept and the slope are as follows, as what we have here. So this will be the corresponding formula. Okay, so given the data below, find the equation of the regression line and provide an interpretation of the result. So as what we have here, we have student A, B, C, D, E, and F. Okay, so A to F. Number of study hours from 2 to 15, and final grade in mathematics we have 79 to 93. So solution, the values needed for solving the equation are as follows. So n is equal to 6, y6, that is a, that is 1, 2, 3, 4, 5, and 6. The total number of hours or summation of x, that is 45. So if we're going to add this one up to 15, that is 45. Summation of y, that is final grade 79 up to 93, that is 517. If we are going to multiply, no, the x and y, so 2 multiplied by 79, that is 158. 3 multiplied by 83, that is 495. 5 times 85, that is 425. 9 times 88, that is 7, and so on. Up to 15 times 90, that is 13595. Then if we're going to add, no, the 152 up to 1395, the total is 3998. So therefore, this will be our summation of x sub y. If we're going to square the x, no, this will be the x. So 2 times 2, that is 4. 3 times 2, that is 3 squared, that is 9. 5 squared or 5 times 5, that is 25. 9 times 9, that is 81. 11 times 11, that is 121. 15 times 15 or 15 squared, that is 225. And then if we're going to add from 4 to 225, the summation of x squared is 465. That's what we have here. Now, okay, so direct substitution. So summation of y, that is 517. Summation of x squared, that is 565. Minus summation of x, that is 45. Summation of xy, that is 3998. Over, our n is 6, right? Summation of x squared is 465. Summation of x squared, that is 45 squared. So, if we're going to multiply this one, 517 times 465, that is 240405. If we're going to multiply the 45 multiply by 3998, that is 179910. Then if we're going to multiply 6 na, multiply by 465, that is 279. Then if 45 multiply by 45, that is 2025. Okay, so if we're going to deduct, no, subtract these two values, we can get 60495. And we're going to subtract these two numbers, we can get 765. So therefore, if we're going to multi or to divide 60,495 divide 765, we can get 79.08. That is for A. Now, if we're going to get the V, no, based on the given example, no, solving the slope B, we can get 0.945. Same, no? Direct substitution, then we multiply, then subtract, then divide. So, hence, the equation of the regression line y is equal to a plus bx is y is equal to 79.078 plus 0.945x, where the slope is 0.9945 and then y-intercept is 79.078. The y-intercept is the value you can get when x is equal to 0. That is, it is the value at the sum point where the line intersects the y-axis. So, based on the given interpretation, no, the marginal change is the magnitude of the change in one variable when the other variable changes exactly 1 unit. So, in the given problem, the value of the slope, which is 0.945, is the marginal change. So, this means that for every change in the value of y, which is the grade, also change at 0.945 unit on the average. Similarly, the value of the y-intercept A is 79.078. This means that the grade of the student would be 79.078 if he or she has 0 hours of study. Okay, so this time, we are going to assist you in understanding the concept of regression analysis, which be composed of the following lessons. Predictions of the value of the different variable given the value of the independent variable, and solving problems involving regression analysis. So, we expect, no, that you will be able to predict the value of the different variable given the value of the independent variable, and you can solve problem involving regression analysis. So, now, this time, you will be learning on how to use the equation of regression line to make prediction on the value of dependent variable. Prediction, or shall I say estimation of the value of the dependent variable in which the value of the independent variable is not present in your data given the circumstances that you have found. So, here's the example. And we have a student A to E, number of hours, and the score. So, we have 1, 2, 3, 4, 5 students. So they have their equivalent number of hours and a score out of 100 items. So before we may proceed with our initial computation, we must remember that in making regression analysis, the data must be correlated and that the correlation must be significant. So, like what we did in the previous discussion, we first need to solve the necessary values in finding the slope and the y-intercept. So, we have n is equal to 5. Then as what we did a while ago, we need to get first the summation of x. So, therefore, we add 5 to 13, that is 44, and this is the summation of x. For summation of y, how do we get 448? So we just simply add 83 to 96, that is 448. xy, you just simply multiply 5, multiply by 83, that is 415. 7, multiply by 87, 609. And so on, up to 13, multiply by 96, that is 1248. For us to get the x squared, no, so 5 multiply by 5 because 5 squared is 25. 7 squared, that is 49. Up to 13 squared, that is 169. And if we're going to add 25 to 169, we can get 428. So therefore, our summation of x squared is 428. Then after that, solving for the y-intercept, a, we can get the a is equal to 75.667. And solving the slope b, same formula as what we did earlier. So we can get slope b is equal to 1.583. Hence, the equation of the regression line y is equal to a plus bx is y is equal to 75.667 plus 1.583. X where the slope is 1.583 and then y-intercept is 75.667. So, the interpretation that the regression line equation our slope b is 1.583, which means that for every change in the value of x, which is the number of study hours, the value of y, which is the score, also changes at 1.583 unit on the average. Similarly, the value of the y-intercept a is 75.667. This means that the score of a student would be 75.667 if he or she has 0 hours of study. Now, since our main objective is to predict the value of y where the value of x is 14, we will now use our newfound equation. We will replace x with 14. So, as what we have here, our y-intercept is 75.67 plus 1583x. So, replacing x and 14, then of course 75.6 rewrite. Then if we're going to multiply this one, we can get 22.64. So therefore, our y is 97.825. Hence, if a student's study hours is 14, his or her expected score in the maths exam would be 97.829. So the data shows the ages of student X in a certain school. And the corresponding number of them having smartphones Y, find the equation of the regression line and predict the number of students with the smartphones with the age of 20. So consider the variables to be correlated and that the correlation is significant. So we have age 13 to 19 and number of students with the smartphone is 19 up to 49. So that this will be your assignment, okay? So our references, of course, that this will be about the regression analysis. So this will be the last topic for tonight. That is the actually we have a two most important topic which is also covered during our comprehensive exam, no? So most of the time, especially for the undergraduate program, no, they are always asking how to choose the right statistical test. No, it maybe Some of you who are very much eager to learn about statistics also asking on how you will be able to choose the right statistical test or statistical treatment. So this topic discuss on how you will be able to choose the right statistical methods or statistical tools for parametric and non-parametric tests. And at the same time, as I mentioned earlier, no, most commonly, this topic, no, also covered during your comprehensive exam. Is about how to choose the right statistical tests. Now, this will be the guide in choosing your statistical tools. In today's statistics, provides the basis for inference in the most medical research. Yet, for want of exposure to statistical theory and practice, it continues to be regarded as the Achilles heel by all concerned in the loop of research and publication. The researchers or the authors, reviewers, editors, and readers. Most of us are, are familiar to some degree in descriptive statistical measures such as those of central tendency in those of dispersion. However, we falter at inferential statistics. This need not to be the case, particularly with the widespread availability of powerful and at the same time user-friendly statistical software. A few fundamental considerations will lead one to select the appropriate statistical test for hypothesis testing. However, it is important that the appropriate statistical analysis is decided before starting the study, at the stage of planning itself, and the sample size chosen is optimum. This cannot be decided arbitrarily after the study is over and data have already been collected. The great majority of studies can be tackled through a basket of some 30 tests from over 100 that are in use. The test to be used depends upon the type of the research questions being asked. The other determining factors are the types of data being analyzed and the number of groups or data sets involved in the study, and I will give you a scheme based on the 5 generic research questions should help. Question number 1. Is there a difference between groups that are unpaired? Groups or data sets are regarded as unpaired if there is no possibility of the values in one data set being related to or being influenced by the values in the other data sets. Different tests are required for quantitative or numerical data and qualitative or categorical data, as shown here in our figure. For numerical data, it is important to decide if they follow the parameters of the normal distribution curve or the Gaussian curve, in which case parametric tests are applied. If distribution of the data is not normal or if one is not sure about the distribution, it is safe to use non-parametric test. Okay? So therefore, we need to identify if parametric or otherwise or non-parametric. When comparing more than two sets of numerical data, a multiple group comparison test such as one-way analysis of variance or ANOVA or Kruskal-Wallis test should be used first. If they return as a statistical significant p-value or using meaning p is less than 0.05, then only they should be followed by a post hoc test to determine between exactly which two datasets the difference lies, repeatedly applying the t-test or its non-parametric counterpart, the Mann-Whitney U test. to a multiple group situation increases the possibility of incorrect or incorrectly rejecting the null hypothesis. So the post hoc or the multiple group comparison test are to be applied in the event that ANOVA or its non-parametric counterpart shows a significant difference, of course, to detect between which two groups the significant differences lies. So example of such tests are parametric data, Tukey's honestly significant difference test, Newman-Kuhl's test, Bonferrone's test, Dunning test, Shep's test, and others. For non-parametric data, we use Dunn's tests. Now, for question number 2, is there a difference between groups which are paired? Pairing signifies that data sets are derived by repeated measurement. This is the before-after measurement for or multiple measurement across time on the same set of subjects. So pairing will also occur if subjects group are different but values in one group are in some way linked or related to values in the other group. Example, twin studies, sibling studies, parent-offspring studies. A crossover study design also calls for the application of paired group tests for comparing the effects of different intervention on the same subjects. Sometimes subjects are deliberately paired to match baseline characteristics such as age, sex, severity, or duration of disease. A scheme similar to figure number 1 a while ago is followed in paired dataset testing. So, as outlined here in our figure 2, once again, multiple dataset comparison should be done through appropriate multiple group test followed by post hoc test. So, again, the post hoc or multiple group comparison test to be applied in the event that repeated measures ANOVA or its non-parametric counterpart shows a significant difference. So, parametric data, either Wilcoxon's, match pair, sign, rank test, or non-parametric data that is Dunn's test or Dunn tests. Now, number 3, is there any association between variables? The various tests applicable are outlined in figure 3 a while ago. Okay? In this figure 3. It should be noted that the test meant for numerical data are for testing the association between two variables. There are correlation tests and they express the strength of the association as a correlation coefficient. An inverse correlation between two variables is depicted by a minus sign. We need to take note that all correlation coefficients vary in magnitude from 0 or no correlation at all to 1 or the perfect correlation. A perfect correlation may indicate but does not necessarily mean causality. When two numerical variables are linearly related to each other, a linear regression analysis can generate a mathematical equation which can predict the dependent variable based on a given value of the independent variable. Odds ratios and relative risk are the staple of epidemiologic studies and express the association between categorical data that can be summarized as 2x2 contingency table. Logistic regression is actually a multivariate analysis method that expresses the strength of the association between a binary dependent variable and two or more independent variable as adjusted odds ratios. So as what we have here for both variables parametric, we use Pearson's R. Otherwise, Spearman's or Kendall's correlations. For the 2x2 data, relative risk, then otherwise chi-square test for trend, logistic, regression. Is there agreement between data sets? This can be a comparison between a new screening technique against the standard test, new diagnostic test against the available gold standard, or agreement between the ratings or scores given by the different observers. As shown here in figure 4, agreement between numerical variables may be expressed quantitatively by the intra-class correlation coefficient or graphically by constructing a bland Altam plot in which the difference between two variables x and y is plotted against the mean of x and y. In case of categorical data, the Cohen's kappa statistics is frequently used with kappa, which varies from 0 or agreement at all to 1 for perfect agreement, indicating strong agreement when it is greater than 0.7. It is inappropriate, no, to infer agreement by showing that there is no statistically significant difference between means by calculating a correlation coefficient. So for numerical data, we use intra-class correlation coefficient or the quantitative method or the bland Altman plot or the graphical method. For the categorical data, Cohen's kappa statistics. Is there a difference between time to event trends or survival plots? This question is specific to survival analysis, or the endpoint for such analysis could be death or any event that can occur after a period of time, which is characterized by censoring of data, meaning that a sizable proportion of the original study subjects may not reach the endpoint in questions by the time the study ends. Data sets for survival trends are always considered to be non-parametric. Again, data sets for survival trends are always considered to be non-parametric. If there are two groups, then the applicable tests are Cox-Mantel test, Gehans or generalized Wilcoxon test, or log-rank test. Log-rank test. In case of more than two groups, Peto and Peto's test or log-rank test can be applied to look for significant difference between time to event trends. It can be appreciated from the above outline that distinguishing between parametric and non-parametric data is important. Test of normality, like Kolmogorov-Smirnov test or Shapiro-Wilk-Goodness of fit test, may be applied rather than making assumption. Some of the other prerequisites of parametric tests are that sample have the same variance. It's drawn from the same population. Observations within a group are independent, and that the sample have been drawn randomly from the populations. A one-tailed test calculates the possibility of deviation from the null hypothesis in a specific direction, whereas a two-tailed test calculates the possibility of deviation from the null hypothesis in either direction. When intervention A is compared with intervention B in the clinical trial, the null hypothesis assumes there is no difference between the two interventions. Deviation from this hypothesis can occur in favor of either intervention in a two-tailed test, but in one-tailed test, it is presumed that only one intervention can show superiority over the other. Although for a given data set, a one-tailed test will return a smaller p-value than a two-tailed test. The latter is usually preferred unless there is a watertight case for one-tailed testing. It is obvious that we cannot refer to all statistical tests in one editorial or discussion. However, the schemes outlined will cover the hypothesis testing demands of the majority of observational as well as interventional studies. So there is no substitute to actually working hands-on with dummy or real data sets and to seek the advice of a statistician in order to learn the nuances of statistical hypothesis testing. Thank you, and I hope that, okay, this will be the references for this discussion. And of course, the ncbi.nlm.nih.gov. Thank you. Okay, so as I mentioned earlier, no, there are certain questions that we need to consider, especially in determining the statistical tools, no, that we're going to use in our research study. So how do we find out, or how do we find out if we choose the correct statistical tools, or how to tell the correct test has been made, has been used, no? Good day, everyone. Our topic for today is about on how to choose the correct statistical test and how to tell the correct test has been used. Okay, so this will be the guide in choosing your statistical tools. So statistical tests are used in hypothesis testing. They can be used to determine whether a predictor variable has a statistically significant relationship with an outcome variables. Estimate the difference between two or more groups, and statistical tests assume a null hypothesis of no relationship or no difference between groups. Then they determine whether the observed data fall outside of the range of the values predicted by the null hypothesis. Now, independent versus dependent variables. Experiments are usually designed to find out what effect one variable has on another. In our example, the effect of salt addition on plant growth. You manipulate the independent variables, the one you think might be the cause, and then measure the dependent variable, the one you think might be the effect, to find out what this effect might be. You will probably also have variables that you hold constant control variables in order to focus on your experimental treatment. The types of the variable, as I mentioned with independent variable, the variable what we that we manipulate as researchers, such as sex, if measuring difference between gender. Dependent variable, the outcome we measure, for example, pretest exams result. So as what we have here, we have independent versus dependent versus control variable. So we have the types of variable, the definition, and the example. Now, types of data. In statistics, there are four data measurements actually, scales, no? Nominal, ordinal, interval, and ratio. So, these are simply ways to subcategorize different types of data. So, the four data measurement scale, of course, we have nominal, ordinal, interval, and ratio are best understood with different examples. So as what we have here, for nominal or categorical, data that fits in the categories with no order. So for example, as sex, na? For ordinal, categories that have an order, like Likert scales. Na? So example is one very happy or a very unhappy, two is unhappy, one is okay, four is happy, five is very happy. This will be an example of an ordinal using Likert scales. So, for example, if the question is, how do you feel today? For example, if the question is, how satisfied are you with our service? One, very unsatisfied. Two, somewhat unsatisfied. Three, neutral. Four, somewhat satisfied. Five, very satisfied. That is also an example of an ordinal. So, as I mentioned, Likert scales. Interval, it must be the difference, no, between points is equal with no 0 point. So, for example, temperature. So, interval scales are numeric scales in which we know both the order and the exact difference between the values. So, as I mentioned, the example of an interval scale is Celsius temperature because the difference between each value is the same. So, for example, the difference between 60 and 50 degrees is measurable 10 degrees as it the difference between 80 and 70 degrees. Interval scales are nice because the realm of statistical analysis on these data sets opens up. So for example, central tendency can be measured by mode, median or mean. Standard deviation can also be calculated. The ratio scales are the ultimate nirvana when it comes to data measurement scales because they tell us about the order. They tell us the exact value between units, and they also have an absolute zero, which allows for a wide range of both descriptive and inferential statistics to be applied. At the risk of repeating myself, everything about interval data applies to ratio scales, plus ratio scales have a clear definition of zero. And good example of ratio variables include height, weight, and duration. So as above but double the value mean twice as much, and zero means absence of the value. So as I mentioned, another example, height and most continuous outcome. We need to remember that nominal variables are used to name or label a series of values. Ordinal scales provide good information about the order of choices, such as in customer satisfaction survey. Interval scales give us the order of values plus the ability to quantify the difference between each one. And finally, ratio scales give us the ultimate order, interval values, plus the ability to calculate ratios since a true zero can be defined. So as what we have here, we need to distinguish types of dependent variables. So for example, if we define that the dependent variable is nominal or ordinal, we may proceed to type of independent variable. Just an internal or interval or ratio, or nominal ordinal. So if it is nominal and ordinal, we can use chi-square of Fisher's exact. But if it is internal or ratio, then we use logistic regression. We need to take note that the chi-square or the chi-square test used to measure differences between categorical data, like 2 by 2 tables, for example. Then the chi-square test does not work well with expected frequency of less than 5 in any cell. It is so easier to use Fisher's exact instead. Logistic regression is more advanced and beyond the scope of this podcast. Seek advice before use. This time, the type of questions. So for example, uh, you identify first the type of dependent variable. For example, if it is interval or ratio. So therefore, we may proceed to ask what type of questions, what type of research question. Then when it comes to type of question, we need to consider that it is an association or differences. We need to take note that this is related to our hypothesis. No? Are you wanting to know that the group are different from each other? So the differences I mentioned. For example, do pretest score differs between males and females? So therefore, you have two tables. The first one is the male and the second one is the female. As you wanted to know if one variable is related to another, that is association. It is duration of sleep associated with pretest score. Now, how about if after identifying the dependent variable, you identify that it's an interval or ratio, then type of research question, you determine that it's an association. Then associations, or this time you are going to look for it is an association or causation. So for example, if that is association, we need to know the person-moment correlation or Spearman's or for non-parametric. Now, which correlation to use? To know this, as with all statistical tests, we need to test the assumptions of the parametric test using person-product moment correlation. Number one, both variables we are testing are normally distributed. So histogram, normality test, or QQ plots. Linear relationship, scatter plot, interval and ratio data, If 1 and 3 violated the U, then use is per month. So it means to say that if it is not agreeable by number 1, so therefore use is per month. If it is violated number 3, use is per month. Okay, but if not, as what we have here, correlation use, persons, moment correlation, or is per month as I mentioned. How about if the this is a causation? So instead, this time we are going to use linear or multiple regression. Now, use regression when the relation is causal. Okay? For example, using height predictor to predict PFRFR. Okay? Outcomes, it would be ludicrous to use PEFR to predict height as height causes PARF, not the other way around. Regression has many assumptions beyond the scope of these discussions. So, type of dependent, we have again, of course, nominal or ordinal, but we are now in the interval in ratio. After defining, no, after knowing the type of question, either association or differences, but if our variables is focused on the differences, so number of group, continued on the next slide, okay? So this one. So number of groups, do you have 2 or more than 2? So it means to say that if you have 2 groups, are groups independent or repeated? If more than 2, are groups independent or repeated? Now, so relationship between groups. Independent, okay, groups are different participants, male versus female. But repeated, measurements taken on the same participant at different points in time. For example, pre-test, pre-exercise test, and post-exercise scores. So, for example, you have a group independent or repeated for 2, okay? And this time that is independent, for example. So what you're going to use? Independent t-test or Mann-Whitney U for non-parametric. So independent groups, we need to know whether we can use parametric independent t-test or non-parametric Mann-Whitney U. So it means to say that if the number of groups are 2, and you are and that is an independent variable, you are you are allowed to use independent t-test for parametric and Mann-Whitney U for non-parametric. Assumptions of parametric test, take note, interval or ratio data, both groups normally distributed, histogram, normality test, and Q to Q plots. Homogeneity of variance or Levin's tests. How about if is repeated? That's what we have here. Repeated measures, we need to know whether we can use parametric. So this time, if that is repeated, no, for parametric, we use paired sample test. For non-parametric, we use Wilcoxon sign rank test. No? Assumptions of parametric test, interval or ratio data, it must be, of course, and the difference between groups are normally distributed either pre-score to post-score. How about if more than two, more than 2 groups, so or multiple groups? So identify if it is independent. Then if it is independent, identify if it is 2 or more or it's just only 1. Okay, for example, you identify already the number of groups as more than 2. Then, are groups independent or repeated? If we use independent, you ask number of independent variables. If your independent variables is 2 or more, use factorial ANOVA. But if you have one, no, dependent variable, use one-way ANOVA or Kroskal-Wallis for non-parametric. Now, for multiple groups, we need to know whether we can use parametric. Again, one-way ANOVA or non-parametric Kruskal-Wallis. Assumption of parametric test, interval and ratio data, of course. Both groups normally distributed as what we did earlier. And at the same time, homogeneity of variance or Levin's test. Same if 1 and 3 violated, of course, same as what we have earlier. Now, how about if we identify the number of groups are more than 2, then the groups are repeated. So therefore, what we're going to use? The ANOVA or repeated measures ANOVA or Priedman's ANOVA for non-parametric. So again, this means testing 3 repeated measurement on the 2 groups or 2 measures on the 3 different groups. Use either parametric, repeated measures ANOVA, or non-parametric Priedman tests. No. So assumption, interval or ratio data, normal distribution, sphericity or tested using Maudsley tests. So this will be the summary. So selecting the correct statistical test is not a mysterious process. It is logical. Take note of it. So we have actually a sequence and some questions to answer for us to identify what specific statistical test, no, that we could apply with our research. Analogous to using clinical guidelines to guide patient treatment. If you want to perform this test on SPSS, we recommend Undisclosed Discovering Statistics using SPSS as a great introductory text. So this will be my references, of course. Thank you very much. Okay, so that this will be the coverage of our statistics. Okay, so as I mentioned earlier before we start, na, that I will give you a final requirements, na. Siguro ano na lang by group. Ang gagawin ko, based sa kung paano nagbibigay ng compre exam. Kasi kailangan ma-prepared kayo. Imagine, nasa first sem yung stat, kasama siya sa exam ng compre. Baka mamaya malimutan nyo na. Kasi ang kadalasan exam sa compre, yung last two na ibinigay ko kaninang presentation, yung paano natin madidetermine kung ano yung statistical tools, kung tama ba ang ginamit natin statistical tools. Then, ang another binibigay na exam sa comprehensive exam is more on ano naman, yung we will give you a published research already. Then what you're going to do is to find out kung tama ba yung statistical treatment, anong masasabi nyo, and so on. Okay?